René Descartes was a famous mathematician and philosopher. He developed the rectangular coordinates, also called Cartesian. Before going into learning about linear functions, it's important for us to understand how the rectangular system works, because later we'll be talking about other systems such as the polar coordinate system and the spherical one. The Cartesian coordinates are based in two axes, a horizontal one, or can call x-axis, and a vertical one called the y-axis. Our idea is to represent the real numbers in both the horizontal and the vertical lines. So what we'll have is, in these lines we'll represent the numbers 1, 2, 3, and so on. And between the numbers 1 and the number 2, we're gonna have all the numbers, so 1.5 and so on. The same will happen between the numbers 2 and 3. And now when we go to the left side, we'll be representing negative numbers. -1, -2, -3, and many more. In the y-axis, we're gonna represent the positive numbers in the top section and the negative numbers in the bottom section. So now what we can do is represent dots in these coordinates. So for example, if I want to represent the number 1, 2, here the number 1 is representing the x-axis and the number 2 is representing the y-axis. These numbers are always going to be in the form of parentheses x, comma, the y number. So when we try and represent, for example, 1, 2, let's start by representing x. We know we have to stand up in number 1. And now from this, we're going to draw a straight line up. And now the y number is 2. So we stand up in the 2 in the y-axis and we draw a horizontal line. And the final number is going to be the intersection of both lines. If I mark, for example, this point here, then the y-coordinate for this number is 3. And the x-coordinate is -1. So then you know that this point is representing the number -1 and 3. Let's now take this linear equation, y equals 2x minus 1, and try to make a plot for it. One way to do this is, first we assign a few values for x, and then we evaluate y equals 2x minus 1 to see what number belongs in the y-axis for each number we have in the x-axis. Let's say we want to evaluate our function in x equals -1, 0, 1, and 2. Now for these numbers of x, we're going to evaluate y. Y equals 2 times x, which is -1, -1. So then y equals -3. Let's try and put this point in our plot. So the point x, y here would be -1, -3. So in the x-axis we had to stand up in the -1 point, and now we draw a vertical line until we get to our number in the y-axis. In this case, -3. So in -3 in the y-axis, we draw a horizontal line. Then this point, the -1, -3, is the intersection. Let's now move on to when x equals 0. If x is 0, then y is 2 times 0 minus 1. This equals -1, and then our point in the plane is going to be 0 minus 1. Let's add this point to the plot. X equals 0 in this line. So it's the vertical line y. And y equals -1. So the intersection is going to be this point. Now when x equals 1, y equals 2 times 1 minus 1, which equals 1. The point is going to be 1 for x and 1 for y. So making this let's add this in the plot. We have 1 for x and 1 for I. This is the point 1, 1. And finally, when x equals 2, y equals 2 times 2 minus 1, which equals to 3. And the point we have to add in the plot is 2 for x and 3 to y. So going to the plot, we draw a vertical line in 2 and a horizontal line in the 3 for y, and we have the intersection is the point 2, 3. So now we have to join these numbers by line. And this is the line that represents the plot. What this line is representing is that for every number that we graph, this one for example, we can draw a vertical line until we intersect the line, and then draw a horizontal line to the y-axis and see what's the point for y, such that y equals this point here times 2 minus 1, because this is the linear equation. Let's now mention a few of the elements that we can find in a plot. We have this number here that is representing when y equals 0. We want to know what number of x such that y equals 0, and we call this number the root for our linear equation. And we also have this number here. This number is representing when x equals 0. So we want to find the number y such that x equals 0. This number is called the y-intercept. Let's start by finding a root. We said that a root was x such that y equals 0. We defined our linear equation as y equals 2x minus 1. So if y equals 0, then 0 equals 2x minus 1. Now adding up on both sides 1, we have that 1 equals 2x, and dividing by 2, 1/2 equals x. And this is our root, because when x equals 1/2, y equals 2 times 1/2 minus 1. 2 times 1/2 is 1. Minus 1 is 0. So this number here is x equals minus 1. Now let's find the y-intercept. We said that the y-intercept was the number that made that x equals 0. Again, we know that y equals 2x minus 1. So when x is 0, we have that y equals 2 times 0 minus 1. 2 times 0 is 0, so then we have that y equals minus 1. And that is this number right here. And something important to notice is that we have that the y-intercept is minus 1. And minus 1 is this number. This is something we'll be learning in future videos, that if we have an equation y equals a times x plus b, then b is going to be the y-intercept. So with this information, we can ask ourselves, is this number a representing something in our equation, in our case the number 2? In this computer-generated plot of our equation, it's easier to see that 0.5 is the root, because when x equals 0.5, y equals 0. And now there's something else we can notice with this. If we take 2 points in our plot, let's say this one and this one, let's see how much we have to move in x and how much we have to move in y. So for the change in y, it's this one. Let's call it delta y. And the change in x, let's call it delta x. So here we know that we started with x equals to 1 in this point, and we finished with x equals to 2 in this other point. So delta x is going to be 1, because we moved 1 unit from 1 to 2. And now in the delta y, we started here with y equals to 1, and we finished here with y equals to 3. So in the y-axis we actually moved 2 steps. We want to find a way to represent this change in y and change to x with a number. The way we're going to do this is by writing the delta of y divided by the delta of x. So in this case the delta of y was 2 and the delta of x was 1. This is 2 divided by 1, which equals 2. Let's say now delete all these drawings with it and take 2 different points. Let's again take this one, the point 1 minus 1. The point 1, 1. But let's now take this one, for example, the point 2.5, 4. The change in y is going to be 4 minus 1, which is 3. It's how many units we moved from 1 to 4. We moved 3 units. And the change in x is 2.5 minus 1. This is 1.5. And it's how much we moved. So from 1 we go to 2, 1 unit, and from 2 to 2.5, 0.5 units. It's 1.5 total units. So now for this other relation, we have that delta y divided by delta x is delta y was 3 divided by delta x was 1.5, and 3 divided by 1.5 is 2. So we grabbed another pair of points, and again we had that the relation in our change between y and x was 2. The same we got in our first calculation, and this one is this number. That's exactly what this number is representing in a plot. Let's go ahead and define this number formally. We define the slope of a line L as given 2 points x1, y1 and x2, y2. The slope m is going to be y2 minus y1 divided by x2 minus x1. So this is exactly what we just did in the example. We had 2 points and we were calculating the delta y and dividing it by the delta x. Let's see another example. Let's say we're given 2 points, minus 3 and 4, and 1 minus 6, and we have to find m, the slope. So what I'm going to do is define this point as x1, y1, and this other one as x2, y2. So with this definition we have that the slope m is going to be y2 minus y1 divided by x2 minus x1. y2 is minus 6. And y1 is 4. Divided by x2 is 1 minus x1, that is minus 3. So now we calculate this. We have minus 6 minus 4 is minus 10, and 1 plus 3 is 4. And this is minus 5 over 2. And now you can ask yourselves, what if I hadn't defined my points like this? What if I had said that x1, y1 was going to be the other point, 1 minus 6, and x2, y2 was going to be minus 3, 4. Well, let's try doing again the calculations for the slope. The slope m will again be y2 minus y1 divided by x2 minus x1. y2 is 4 minus y1, which is minus 6. And this is divided by x2 is minus 3 minus x1, which is 1. So doing this calculation, 4 plus 6 is 10, and minus 3 minus 1 is minus 4, and this is minus 5 over 2. So it doesn't really matter how we define x1, y1 and x2, y2. What matters is what we are doing, this subtraction of the second one with the first one in y and the second one with the first one in x. Because we'll get always the same answer. Let's now try and solve this other example. We're giving the slope of a function that is 3/2, and we know that our function has a point in 1, 1. We have to draw the complete function. So let's start by marking this point in our plot. 1, 1 is here because x equals 1 and y equals 1. Now remember the definition for the slope. M was the delta in y divided by the delta in x. This was the change in the y-axis divided by the change in the x-axis. And we are told this number is 3 divided by 2. So delta y is 3 and delta x is 2. So what we have to do is, from our point, we have to move 2 units in the direction of x. So here we are in the number 1, we move 1 unit, 2 units, and we end up in the number 3. And now we have to move 3 units in the y direction. That is 1, 2, 3. And our next point is 3 for x and 4 for y. And 2 points are enough to generate a line. So with these 2 points we can already go ahead and plot our function.